Good morning. I'm showing 9 o'clock. We're going to go ahead and get started. My name is Mike DeLacluse. I'm the president of the Lesman Instrument Company. I'd like to thank you all for taking time out of your busy schedules to join us for Fixed Gas Detection 101. Today we have Charles Simek of Honeywell Analytics presenting a 101 level foundation on fixed gas detection. In this webinar, you'll learn about the different gas detection technologies, some strengths and weaknesses of each, some common gas hazards and gas detection applications. You'll also learn about some of the applications, some different technologies used to detect combustible, toxic, and asphyxiate gases. And then at the end, we'll have time for some of your questions. Charles has worked in the industrial fire and gas detection safety industry for 30 years, serving as an electronics technician, technical writer, sales manager, business development manager, and product specialist. He's also been a member of the NFPA building safety section for the last 14 years. Charles is a subject matter expert and product technology specialist for electro-optical flame detectors and is working for the Honeywell Analytics marketing team on their premium line of fixed gas and flame detection equipment. We will be muting the phone lines. If you have a question, there is a chat tool built into GoToWebinar. Please just go ahead and enter the question in there and I'll make sure they get answered. With that, I'm going to turn it over to Charles.
Thank you, Mike. Appreciate that. Good morning, everybody, and welcome to Honeywell Analytics presentation on gas detection fundamentals. So this module is going to provide you with a fundamental knowledge of gas detection. We'll define gas and discuss the hazards associated with it. We'll also learn some key industry terminology along the way. We'll then examine the technologies that are used to detect gas. And then finally, we'll kind of close up with a summary of key takeaways. So a gas is a state of matter defined as a substance processing what we call perfect molecular mobility. Unlike a solid or a liquid, it has the property of indefinite expansion. So the name gas comes from the word chaos because gas molecules move randomly and chaotically. Gases can move at very high speeds and mix very rapidly into any atmosphere in which they are released. There are three main types of gas hazards: flammable or explosive gases that can ignite or burn and possibly result in property damage, personal injury, loss of life, and or destruction to the environment. The word toxic is more or less synonymous with poisoning in everyday usage. Exposure to toxic gases may result in physical harm or loss of life. And finally, asphyxiates displace oxygen, creating a risk of suffocation. Symptoms of asphyxiation include dizziness, lightheadedness, unconsciousness, and even loss of life. Let's begin with a closer look at combustible gas detection. So when referring to gases that are potentially combustible, the concentration level is critical. The term lower explosive level is defined as the minimum amount of gas that must be present in air to become combustible or to ignite. A gas concentration that's below this level is considered to be too lean to ignite. The term upper explosive limit is defined as the maximum amount of gas that must be present in air in order to ignite. Concentrations that are above this level are considered too rich to ignite. So mixtures of gases and air that will burn only within the flammable or explosive range boundaries that are defined by the upper and lower limits, okay? This region is considered the explosive or the flammable range. It's worth noting that some refer to these upper and lower flammable limits as UFL and LFL. So UFL is synonymous with UEL, and likewise LFL is synonymous with LEL. Gas concentration is expressed either as a percentage by volume or a percent LEL. For example, 100% LEL methane is equivalent to 5% by volume in air. We're going to go to the next slide for some more examples of combustible gases and their upper and lower explosive limits. There are a variety of combustible and flammable gases, and these are just a few that include propane, hydrogen, methanol, ethane, ethanol, methane, or what we call natural gas. But like I had indicated, there are many other flammable gases that are available. So the second hazard we're going to discuss is toxic gases. These gases could cause illness, discomfort, physical harm, may even threaten the life of those whom they are exposed to. So when referring to gases that are potentially toxic, the concentration level is critical, but so is the length of time that a person may be exposed. In the gas detection industry, you'll often hear about the permissible exposure limits, or PEL. This is the limit for exposure to a specific chemical substance, okay? Permissible exposure limit is a concentration level usually expressed as a time-weighted average, okay? So this is the amount of time that you're allowed to be exposed to that specific level generally throughout your working day, so it's usually 8 hours, okay? Some toxic gases may have permissible exposure limits that are safe for shorter periods of exposure time. So you'll encounter short-term exposure limits, or STEL. These are also synonymous with ceiling limits, and this is generally for a 15-minute period of exposure. The TLV, or the threshold limit value of a chemical substance, is the permissible exposure limit to which a worker can be exposed to day after day for a working lifetime without adverse effects. And then finally, the IDLH, or immediate danger to life or health. This is the most dangerous level for toxic gases. So the permissible exposure limit, time-weighted average, short-term exposure limit, threshold limit value, and immediate danger to life or health, which we just discussed on the previous slide, are usually expressed in parts per million or parts per billion. As an example, if we fill a room up with 1 million balls, and one of those balls was red, that would represent 1 part per million. 1 of a million balls is red, so it's 1 ppm. Typically, if we change the million to a billion, then the 1 red ball would be 1 part per billion, or 1 ppb. So this is kind of a list of some of examples for toxic gases: ammonia, carbon monoxide, chlorine, hydrogen sulfide, nitric oxide, nitrogen dioxide, and sulfur dioxide are some of the more prevalent gases that you're going to find in chemical and petrochemical environments. There are others. There's many others for toxic gases. There's hydrogen chloride, there's hydrogen cyanide, there's phosgene. There's many other gases that can be detected. And the third group, the third hazard, is asphyxiates. And as a general rule, there are a wide variety of gases that fall into this category. Asphyxiates are commonly called silent killers because these gases deplete oxygen, resulting in possible suffocation. As previously mentioned, exposure to these gases may cause dizziness, nausea, loss of consciousness, and even death. Okay, now that we've covered the 3 basic gas hazards, let's take a little bit of a look at the typical areas where we would require gas detection. Here are just a few. Food processing. Food and beverage processors can use and produce dangerous gases. Gas detection may be required in both traditional and renewable power generation. Traditionally, fossil fuels like coal, oil, and natural gas have been used to generate electricity. Today, renewable energy is becoming a key aspect of power generation, with wind power and biogas becoming more prevalent forms of power generation. Water purification and sewage treatment plants produce a variety of toxic and combustible gas hazards. Many industries use refrigeration as part of their process, from food and beverage manufacturing, gas liquefaction, chemical manufacture, to cryogenics and liquid natural gas shipping. In these environments, it's essential to ensure that ammonia does not build up, causing potentially toxic and/or explosive atmospheres. Laboratories and medical facilities like hospitals may use a variety of flammable and toxic substances. Very large installations may also feature their own on-site utility supplies and backup power stations. And finally, exhaust fumes can build up in parking garages and tunnels, creating toxic gas hazards. Gas detection is used to monitor the buildup of these gases like carbon monoxide, methane, and also control the ventilation system. In addition to these areas of gas detection, gas detection may also be required for building protection in the aviation industry, for planned equipment modifications, clandestine labs, confined spaces, perimeter monitoring, and painting, just to name a few. Okay, so now that we're familiar with some of the areas that might require some gas detection, let's talk about the technologies that are used to detect the presence of gas. So when detecting combustible gases, the technology begins with a catalytic bead sensor. So we start with a platinum wire coil surrounded by an alumina ceramic base. Then an outer coating of palladium or rhodium is applied to the base, forming a catalytic bead or pellister. Now, when combustible gas air mixture passes over this hot catalyst surface, combustion occurs and the heat evolved increases the temperature of the bead. This in turn alters the resistance of the platinum coil. This process requires the presence of oxygen in order to combust the gas as it passes over the catalytic bead. Sometimes changes in the environment will affect the resistance of the catalytic bead, such as hot or cold temperatures. Additionally, humidity will affect the resistance of the catalytic bead sensor. So a single catalytic bead sensor represents half of our sensor. To compensate for these changes in temperature and humidity, a second bead or pellister is added. The second bead is produced so that it does not respond to the presence of combustible gases. When there is no combustible gas present, the relative resistance of the coils is equal. However, when a combustible gas air mixture passes over the hot catalyst surface of the beads, only the sensitive bead changes, resulting in a difference in resistance. That difference is measurable. And that's how the catalytic bead sensor works. Catalytic bead sensors interact with the target gas, making them susceptible to poisoning. Poisoning occurs when components containing combustible compounds come in contact with the catalytic bead. Silicone is an example of a poison for a catalytic bead sensor. Silicone ends up remaining on the catalytic bead, making part of the surface unusable. Over time, repeated or continuous exposure may desensitize the catalytic bead sensor to combustible gases. Some advantages of catalytic bead gas detection are that it's relatively low cost, it's accurate and linear over sensor detection range relative to the calibration gas, utilizes a broadband sensor, has a long history with a proven track record for the technology. A few of the limitations are it leaves you unable to actually identify the type of gas being detected. Also, it requires sufficient oxygen to support the catalyst process. Has a high power consumption. Sensors are vulnerable to being poisoned, and combustible gas readings may not reflect the true concentration of the gas hazard that's present. Some flammable gases will react with infrared energy and some will not. Hydrocarbon gases will absorb infrared energy. So hydrocarbon gases are considered to be infrared active, whereas hydrogen will not absorb infrared energy, and therefore it's considered to be infrared inactive. So the IR method is used for hydrocarbon gases that are flammable, but not for all flammable gases. The technology is based on absorbing hydrocarbon gases, not non-hydrocarbon flammable gases. It's important to note that the target gas does not have to come in contact with the sensing elements like it does with the catalytic bead sensor, nor is the target gas changed or consumed by the process. Therefore, this method is inherently immune to the typical poisoning that's associated with the catalytic bead technology. Additionally, we don't require the presence of oxygen in order to detect hydrocarbon gases. Just like with the catalytic bead, though, IR absorption method is affected by changes in the environment, temperature, pressure, and humidity. Therefore, an additional IR wavelength is incorporated to compensate for the changes in the environment. This additional reference wavelength is at a different frequency than the sample wavelength, and therefore it will not be absorbed by hydrocarbon gases. But the two wavelengths will track changes in temperature and humidity and pressure. The only difference coming in when there's hydrocarbon gases present. So the absorption wavelength is known as the sample wavelength, and the wavelength at which no absorption is expected is known as the reference wavelength. The measurement made is the change in ratio between the sample and the reference signals. And so you can see when we don't have any gas present, both the source or sample and the reference signal are strong. As fog, dirt, or rain or other environmental changes occur, both signals are affected equally. Only when there's gas present, though, is there a difference between the sample and the reference wavelength amplitude. And this is where we can actually measure the amount of gas that's present. So some of the advantages for infrared gas detection are that it doesn't require the presence of oxygen. Sensors are not affected by typical poisons or inhibitors. They have low power consumption when compared to the catalytic bead sensor. They are very accurate, very stable. The sensors are available for 100% by volume methane. And sensors have a 5-year mean time between failure, resulting in a lower cost of ownership over the lifespan of the sensor. Some of the limitations for infrared gas is that we can't detect hydrogen, we can't detect acetylene or carbon disulfide. They are more expensive than catalytic bead sensors. They are affected more by changes in temperature and pressure. And their response is linear to methane, but non-linear to other hydrocarbons. So you're going to be linear to the gas that you calibrate to, but if you calibrate to methane and propane comes along, your reading is not going to be accurate. This is a different technology. This is a photoionization detector. So as organic materials decay and break down, they release volatile organic compounds in the form of VOC gases. These gases represent combustible and health hazards if they accumulate in sufficient quantities. Photoionization is the technology that was developed to sense these VOCs, and we use ultraviolet energy to initiate that ionization process, which basically releases electrons, and when you do that, you create ions. You create a positive ion and you create a negative ion. As VOC gases pass through and by the UV lamp, the UV energy causes one or more negatively charged electrons to be released from the molecule. This creates an ion, a positively charged particle. The VOC is considered ionized in this state. The electrons of the ionized gas will be attracted to the positively charged anode electrode, while the ions will be attracted to the negatively charged cathode plate. This migration of electrons and ions results in a current pulse. The frequency of that pulse is proportional to the gas concentration of the VOC that has been ionized. A small pump is used to draw the VOC gas into and through the detection chamber. This pump also forces the ionized gas away from the cathode and the anode, allowing the electrons and the ions to reform as the original VOC gas, and then it's exited back out to the environment. So whether or not a gas will ionize in the presence of the UV lamp is dependent upon what's called the ionization potential, or the EV of the actual gas. EV stands for electron volt. Now, using a UV lamp with a 10.6 EV output, gases with an ionization of 10.6 EV or less will ionize. Gases with ionization values greater than 10.6 EV won't ionize using that lamp. Okay, so all of our atmospheric gases that we have listed at the top here, nitrogen, oxygen, argon, carbon dioxide, these are the major constituents of our atmosphere. Their EV, you can see, is greater than 12 in just about every case. So none of our atmospheric gases are going to be ionized by the 10.6 EV lamp, which is good because we don't want our sensor going off to normal air that we breathe. As you can see, ammonia and benzene, ethanol, hydrogen sulfide, isopropanol, xylene, O-xylene, and P-xylene all have ionization potentials below 10.6 EV. Therefore, all of those gases can be detected using the photoionization detector. Okay, some of the advantages of using PID are that it is sensitive to ppm levels. It's accurate and linear over the sensor detection range. It doesn't require the presence of oxygen. The UV tube is self-cleaning or self-scrubbing due to the creation of ozone by the detector. So when the pump is turned on, there's generally a 50% duty cycle. As the pump is pulling in, it's leaving ozone on the surface of the lamp. When the pump is turned off, that ozone actually that's been accumulating on the lamp allows it to scrub the lamp and keep it clean. Okay. Some of the limitations for PID gas detectors are VOC is usually detected by means of broad range sensors. So the broad range sensors provide overall reading for the general class or group of chemically related contaminants, but it's not going to be specific. Okay, we're unable to identify the specific type of gas being detected. Okay, and then the sensor maintenance may be required. This is an optical method, much like the IR, but unlike the IR, because we're drawing a sample, that means we're pulling in things like humidity and dirt and debris, and unless we're filtering those on the front end, we have to get in and actually clean our electrodes, and we have to clean our UV lamp if it becomes too dirty. So let's switch gears and talk about technologies used to detect toxic gases. So gas-specific electrochemical sensors can be used to detect the majority of common toxic gases, including carbon monoxide, hydrogen sulfide, chlorine, and sulfur dioxide, among others. And we use these in a very wide variety of applications. Go back up. Additionally, electrochemical cells are used for oxygen depletion or oxygen enrichment applications. Electrochemical cells are compact, require very little power, exhibit excellent linearity and repeatability, and generally have a long lifespan, typically 1 to 3 years. Commercial designs of electrochemical cells are numerous, but share many common features. Active gas diffusion electrodes are immersed in a common electrolyte, frequently a concentrated aqueous acid or salt solution. And this creates efficient conduction of ions between the working and the counter electrodes. Okay, we have an advanced design of electrochemical cell. This is the one that I just spoke about, where we have a single carbon filter, which is also a hydrophobic membrane. So the molecules will diffuse into the electrochemical cell one at a time. As they are in the electrolyte reservoir, that's where we're going to get our ion migration from the counter to the working electrode. And then, of course, we can measure that current change using the output pins. So, but in addition to this, we have a different electrochemical cell that we manufacture just for Honeywell. And it's called Honeywell's patented SureCell technology. It overcomes some of the deficiencies of commercially designed electrochemical cells. SureCell incorporates a smaller, more sensitive primary reservoir and an additional expansion reservoir. Now, having two reservoirs gives us a couple of advantages. If we go back to the previous version where it has just a single electrode, because the membrane is hydrophobic, it's going to allow humidity to pass through. And if enough humidity gets into this cell, it could possibly burst or rupture and thereby making the sensor inoperable. Similarly, if you use this in a very low humidity environment, because it is a hydrophobic membrane, the moisture from the electrolyte reservoir will be pulled out into that drier humidity environment. Now, if enough of that moisture gets pulled out, we end up with a very acidic electrolyte, and that's going to, over time, consume the counter electrode and the working electrode. With this design, the primary electrolyte reservoir is small. So we have a working electrode and a counter electrode. And then what we have is a wicking element that will go down to the expansion reservoir. And the expansion reservoir, we show it full here. Generally, it's halfway full. To allow excess humidity that makes it into the primary reservoir, it now has some place to go. It has that expansion reservoir. And so we're not rupturing or exploding this particular cell. Similarly, as the primary electrolyte reservoir gets depleted due to the presence of very low humidity levels, that wicking element that I mentioned earlier allows us to draw from the expansion reservoir to replenish the primary electrolyte reservoir. So we're not having an acidic environment that we're using. Also, having a very small reservoir actually increases our sensitivity to many of the gases. Okay. Okay, some of the advantages of electrochemical cell technology. It's relatively low cost, sensitive to part per million concentrations, accurate and linear over the sensor's detection range, typically fail-to-safe operation. So some of the limitations include cross sensitivities. The big ones that I know of are between CO and hydrogen. Also, you may see response to other gases than the target gases. That kind of lines up with the cross sensitivity. Electrolyte contamination by substances such as alcohols or citrus oils. That's actually going to change the pH of our electrolyte. And then some of the sensors are very sensitive to humidity and temperature. For example, nitric oxide and ethylene oxide sensors are very sensitive to changes in the environment. Last technology that we're going to talk about, I think it's the last, is ChemCassette, or what's called paper tape technology. Okay, it's based on the use of an absorbent strip of filter paper acting as a dry reaction substrate. So this performs both a gas collection and a gas analyzing media, and it can be used for continuous monitoring. Right. So the system is based on colorimetric technology that is capable of extremely low detection limits for a specific gas. It can be used very successfully in a wide variety of high toxic substances, including diisocyanates, phosgene, chlorine, fluorine, and a number of hydride gases employed in the manufacture of semiconductors. The stain intensity that occurs on the paper tape is measured with an electro-optical system which reflects the light from the surface of the substrate to a photocell located at an angle to the light source. So as the stain develops, the reflected light is diminished and reduced, and the reduction of the intensity is sensed by the photodetector in the form of an analog signal. This signal is converted to a digital format, then presented to the presented as a gas concentration using an internally generated calibration curve and the appropriate software library. ChemCassette, that's kind of the name of this technology and the name of the actual detection media. ChemCassette formulations provide a unique detection method that's not only fast, it's sensitive and specific, but it's also only available system, it's the only available system which leaves physical evidence that a gas leak or a release has occurred. As sample gas molecules are drawn through the ChemCassette with a vacuum pump, they react with the dry chemical reagents and form a colored stain specific to that gas only. The intensity of the stain is proportionate to the concentration of the reactant gas. The higher the gas concentration, the darker the stain. Makes sense. Some of the advantages of paper tape gas detection are its measurement sensitivity. It is specific to the target gas, its accuracy and its linearity, and there are a wide range of tapes available. Some of the limitations for paper tape are tapes are time sensitive. In other words, they have a shelf life and can be sensitive to changes in temperature, pressure, and humidity. Primarily used in the semiconductor industry, but it is one of the technologies that we wanted to discuss today. So generally, those are environmentally controlled applications. So kind of a quick summary is that we've gone over the three types of gas hazards: flammable or combustible, toxic, and asphyxiates. We've talked about catalytic bead sensors. We've talked about non-dispersive infrared and how photoionization detectors work. We've talked about the electrochemical and the paper tape technologies, or ChemCassette, that can be used to detect toxic and asphyxiate gases. Okay, there are advantages and disadvantages to each of these detection techniques. Catalytic bead detectors are simple, low cost, but sensors can be poisoned. Electrochemical cell detection allows for the detection of a wide variety of gases, but failure modes aren't revealed unless advanced monitoring techniques are used. And then infrared detectors don't require the presence of oxygen and are unaffected by typical poisons or inhibitors that might affect a catalytic bead sensor, but the cost is a bit more than a catalytic bead sensor, and It's affected more by changes in temperature, pressure, and humidity. Photoionization detectors do not require the presence of oxygen, but are unable to identify the specific type of gas being detected, and sensor maintenance may be required. When we say sensor maintenance, generally it's above and beyond what we would normally have for a catalytic bead or an IR sensor. Paper tape detectors are highly sensitive and selective to toxic gases, but are also complex and expensive. Additionally, the paper tapes do have a shelf life. So make sure you conduct a thorough analysis of your site in order to determine the most suitable gas detection technique or technology to employ. And that is the end of my presentation. Thank you for...
All right.
Oh, go ahead.
Charles, thank you very much.
Yes.
As we do wrap up, if there are any questions, the audience can go ahead and type those into the chat tool, and we'll make sure that we get them answered. We should also let everybody know that we have a product specialist on staff, John Gravel, who's been around this stuff for 20 plus years and is very good at making sure that the application, that the right product fits the application, and that the applications will work. So, Charles, thank you very much for your presentation. Again, if anybody in the audience has any specific application questions, feel free to give us a call at 800-9-LESMAN. If you do not know your account manager, feel free to ask for me, Mike D. Lecluse, and I'll make sure that you get taken care of. You can also reach me at miked@lesman.com. We do have a question that came in, and the question is, can you comment on detection of oxygen and the impact of relative humidity on those sensors?
So the oxygen sensor does not use that SureCell technology that we spoke about earlier. It uses the this technology. And so when we talk about humidity and oxygen, humidity is a very real danger for this cell. And when we're trying to talk about oxygen depletion. So generally the oxygen sensors are 0 to 25% by volume, with 20.9% by volume being normal atmospheric oxygen, what we typically breathe. We'll set our first alarm point if the oxygen drops below 19% by volume. That's generally when you start experiencing symptoms, the dizziness, the nausea, the lightheadedness. You can even pass out at that point. We have a second alarm level that we set at 23% by volume. This upper level, or this rising alarm level, is associated with 23% by volume because that level of oxygen and higher makes typical materials more flammable, easier to combust. At 25% by volume, it doesn't take much energy for your clothing to catch fire. And so that's a real concern. If you guys, I don't know if you guys remember the Mercury program that NASA had, and we lost 3 astronauts because their oxygen level within the cabin on the launch pad rose to extremely high levels, and there was an ignition or a spark from a relay component, and that caused ignition, and we lost 3 astronauts on the launch pad. So I hope that answered your question.
Okay. Next question we have is, does the I'm assuming it's electrochemical sensor, eventually get full of the sensing gas?
No. So when we have the migration, and it's simply a single molecule at a time. So as the molecule enters the electrolyte reservoir, one molecule portion of that reservoir gets consumed because we have the transfer of current between the counter and the working electrode. So we're not worried about the electrochemical cell filling up with gas as much as we are with it filling up with other stuff that's not going to allow the migration of ions from the counter and the working electrode.
I always think of it as like a battery. And
Yes.
the more gas that it gets exposed to, the faster it consumes the electrochemical cell.
The electrolyte, correct.
Yes, yeah, exactly. So, if you think of it like a battery, it's pretty easy to comprehend.
The catalytic bead sensor and the electrochemical cells, these are consumable technologies. The more the target gas is exposed to them, it results in basically a reduction of life.
Right, and they are consumable and can be bought as a separate part and replaced. And I think there's alarms built in to make sure that you're not running with a cell that's dead. Am I right about that?
Correct. Yes.
Yep.
So yeah, when we talk about specific products later, in other modules, there's something called reflex technology, and reflex technology basically pings the electrochemical sensor every 8 hours, and the strength of the response to that pinging of the sensor, we can determine how much life is left. And when we get to a point where we feel that there's only 30 days left, the sensor will actually generate a warning, and that kind of prompts you to go ahead and purchase your next replacement cell.
Right. All right, that is all the questions we have for now. So we'll continue to wrap up. And again, if anybody thinks of a question after this session is over, please feel free to email it to me at miked@lesman.com, and I'll make sure that it gets answered. If you want to know more about these technologies, all of our webinars are posted to both our website and our Lesman Instrument Co. YouTube channel, so they can be watched at a later time or shared with other employees. If there's some topics that you would like us to cover in our webinars, please send me an email with the subject. We have access to lots of product and process specialists, so let me know what you'd like covered, and we'll make sure that we get it lined up. At this point, we are talking about putting together a 201 level course or webinar on gas detection, and that will probably happen sometime in December, so watch your email for that. At this point, I don't have any further questions, so we will conclude our presentation. Thank you all very much for attending, and Charles, thank you again for your presentation. It was great.
Mike, thank you for hosting. We appreciate it very much.
Oh, we do have one other question that popped in.
That's
Somebody
fine.
beat the wire. What portable equipment would you recommend to use for emergency response? Boy, that's a great question.
Yeah,
and a broad one.
So when it comes to portable gas detection, it's all going to be dependent upon the hazard. Typical first responders, as a minimum, are going to use what's considered a classic 4-gas detector. It's going to be combustible, oxygen deficiency, carbon monoxide, and one other gas. It could be hydrogen sulfide, it could be ammonia, but typically a 4-gas monitor is generally used, and that's typical throughout the industry for portable gas.
That fourth gas is somewhat selectable, right?
Yes, it is.
Depending on what you're
like in the oil and gas industry, it's generally hydrogen sulfide.
Right. And then the next question is, are there sensors? Are the sensors either class division rated or ATEX rated?
Yes. So, and there's we meet the requirements for North America and for Europe and for Asia separately. They'll have separate approvals. So for most of our products that I deal with in the industrial premium portfolio, we're class 1, DIBS 1 and 2, groups B, C, and D. When we talk about Europe, that's generally an EXD or flame-proof, and it can be either IB or TB, depending upon the requirements of the specific application. IB is intrinsically safe. And then generally followed by, I think it's 2C plus H2 for most of what we do. with anywhere from a T4 to a T6 temperature rating.
Great. Okay. I don't have any further questions at this point. So again, if someone in the audience thinks of a question, feel free to email it to me and we'll make sure that we get it answered. Charles, thank you very much. With that, I think we'll go ahead and conclude.
Yep. We will be speaking later, Mike. Pleasure.
All right.
Thank you, guys.
All right. Thank you very much. Yep.
Okay.
Bye.